So first I would like to thank the Kavli Institute, KITP, for hosting us, but also for hosting several programs which are related to neural computation, neuroscience, and machine learning, starting actually from the first program in 1986 on spin glasses, computation, and neural network, which was directed, co-organized by John Hopfield and Peter Young. And the theme of this kind of formative program and the theme of our program and today's lecture is really very, very much relevant. So I want to give you some brief historical context of this statistical mechanics of learning. So we all know the Hopfield model, recurrent neural network working as an associative memory. The StatMech was a StatMech of the phase space of neurons in this case. What I would like to just highlight the fact that in this statistical mechanical framework, the landscape of the neural phase space is rough, is something in between a simple mean field ferromagnet and a spin glass. Minima, local minima, etc. We needed the replica theory to actually compute the properties of such systems. Finally, and including replica symmetry breaking and all the glorious properties that come together with this. A few years later, in 1988, a seminal work by Elizabeth Gardner introduced statistical mechanics in weight space. This is for a single layer perceptron as a classifier and with n weights, and the statistical mechanics that she developed was about the effect of learning on the volume of weight space. Again, replica was used, but in this case the landscape is convex, and therefore there is no phase transitions, and replica is replica symmetric. In both cases, there's commonalities. For instance, the scaling of the data size, how many examples, how many memories you have, scales linearly with the size of the system. This kind of the relevant, found out to be the relevant action in the thermodynamic limit. Also something common that in order to solve actually the problem, both problems, although they are different, but one needs to make very simplifying assumptions about the data, memories, or input or the input-output relations. Basically, they're IID binary or IID Gaussian, but that otherwise either the system fails to work or the theory fails to work. But so we need to make these very strong assumptions about the data, structural data. Okay, so this is in the 80s, and since then, of course, many of us have been busy trying to extend this to multi-layer systems, particularly Gardner theory, which is more related to learning in general. And then once you go to multi-layer system, things become, all hell breaks loose. What we found is, it's non-convex. There is a kind of spin glass replica symmetry breaking phenomena. Landscape is rough, local minima, etc., etc. The theory was hard, but also the system was not a nice system to work with. All right. So this was kind of in the 90s and 20s, and at the same time, machine learning also had trouble with extending learning to multi-layer perceptron. There was the backpropagating algorithms, but what the heck is doing? Finding local minima, how to interpret the solution. And what are the success of this algorithm? So this is where the field was for several decades. Now we all know the revolution for deep learning and changed not only, of course, our life in terms of the success of this machine learning in many applications, but also a theorist. It changed our life in the sense that there are new challenges, but also new perspectives on the problem of learning in deep systems. And some of them are quite surprising and counter to what we the intuition of the old theory of the 80s and 90s, and I'll come to it in a moment. Okay, so deep learning is learning in general deep structures, multi-layer structures. There are, of course, many of them, and the modern ones are complex, transformers, and all kinds of other elements that they have. So we are far from having any glimpse of theory for these more complex and modern architectures. Of course, part of the challenge in this program is to make these advances, but I'm going to describe some advances in the theory of deep learning in the simplest structure. And that's what I want to describe to you today. We'll see how much I'm covering. Okay, so what is the structure? It's a very simple multi-layer network. I'm going to define it. So you have input layer. These are each node is a neuron. You have x1 up to x, let's call it n0, the size of the input layer. You have some connections here, fully connected systems. So let's call it W1. W1 has n neurons. I'll define them so soon. Then you have another layer. For simplicity, we'll assume it has the same size. And again, some matrix W2 here, etc. And then we come to the top layer, N, and this will be then WL, the top layer. And then for simplicity, I'll assume there is only one output node, which we'll call it F, you'll see in a minute. And this output node is connected linearly to the top layer and with the weights A. So these are matrices. This is a vector of size n, and F is the output of the system. So you put a vector in the input, you propagate it through the network, you compute the output, and you compare it to the target output. Okay, so what each neuron is doing in this network. So each neuron is, let's call it XL, the L's layer. So XLI, the index of the neuron in the L's layer, is some linear function of its input, ZIL, okay? And the input ZIL is defined as 1 over square root of n times sum over j times its input weight, Wij of the layer L, times the previous activation, xj L minus 1. So we call this pre-activation, or the field going onto the neuron. There's this may be linear, maybe nonlinear, some nonlinear function, and then this defines the activity of each one of the neurons. So it's a very simple neuron. It's a feed-forward propagation. You do weighted linear sum. You have nonlinearity. You have the activation, and you go to the next layer. Very simple. The output is the same, except that the output will be linear. So F will be simply 1 over square root of n times sum over I from 1 to n of AI times XIL, the output, the feature layer. So this is important. This is the feature layer, it's called. And these are important layer because they are the layer that directly read out by the output in a linear fashion. Okay, so that's a very simple. So the system here is linear. The output is linear. Here, all the neurons, the hidden neurons may be linear or may be nonlinear. So that's what phi would be. Okay, so that's the system. Okay, so with this system, what are we interested in? So we're interested in what is what kind of a function is defined in this network. So you have some arbitrary input x, or denoted by x, without superscript as the input to the system. So we are interested in f of x. So this is f of x, basically, right? So f of x. Arbitrary input x, propagating, this is the output of the system. So the system with a given set of parameters defines an input-output mapping. So this is f of x. And this, of course, will be a function of all the parameters of the system. I'll denote the parameters by theta. Theta is the collection of all the hidden layer matrices times the output vector. W is all these collections of W, A is the readout weights. So this is now what's known as the predictor. The network predictor. The network predictor for every input x, what should be its output? Or what is its output? Yeah? Is what? Yeah. Phi is fixed for all, yeah, for simplicity, phi is fixed for all of them. I'll take the simplest case where phi, basically where phi of z is z, this will be the linear case, or phi of z will be relu of z, which is the rectified linear. So relu would be this. This is z and this is phi, or linear. Okay, more questions? That's the system. Okay, so now what does it mean to learn the system? Learning here. So we define, so we have examples. So we have our data. We have a pairs of input and labels. The target output, mu goes from 1 to p. And now we have a loss function, which is a function in weight space. Okay, so it's a function of theta given the data, which we'll use as mean square error, so sum over mu from 1 to p of f of x mu theta minus y mu squared. Right, so the predictor of the network, the output of the network for each one of the input in the data compared with the output is a mean square error. That's the system. Okay, so what does it mean to learn here? Well, first of all, we want to somehow find theta that minimizes this loss on the training data, and I'll come to it in a moment. But as you all know, we are also interested in, so let me define training is some process by which we minimize or approximately minimize L of theta given the data. That will be the training, okay? But we are all interested in, of course, generalization. We're interested in, after we train the data and we find theta star, what happens if you put a test point here and whether the system will predict correctly its output. So this is what's known as generalization. So let me define it. For a given test input, x, which is not, in general, not part of the training data, we want to measure the error. So this will be 1/2 times the predictor of the network given, we find theta star after training. So we have here theta star, the one that we found by training, minus the correct output, if we know what it is for this, and this will be our measure of the generalization error. Now we can average over many test points and average over many training data and so on, but that's basically the thing which we are interested. We are interested, having done the training, whether the system will generalize well to new data. Otherwise, it's not interesting. Okay? Is this clear? Very good. Okay. So what are the general questions before we try to do StatMech? The general question here are several, and that's kind of at the core of learning, of theory of learning. What are the questions? So questions, one big question is capacity, right? We want to know whether the function that we want to learn in this system, the system is large enough or complex enough to do the job. So large enough means here, maybe the width, maybe the depth, L is the depth, N is the width, nonlinearity, etc. Is it good enough for the kind of problems that we're interested in, object recognition, language, or whatever, okay? So we can call it capacity, without defining it too precisely. Now, the second, so this is about architecture. The second question is the training, basically the dynamics. This has to do with the landscape in statistical physics terms. Okay, so is it, how easy or hard it is to find a good theta that given the data, okay? So that's the landscape issue. And the second, and the final issue is generalization versus overfitting. Okay, what is the point with overfitting? The point with overfitting is that if I have for a fixed amount of data, I can always choose a sufficiently big network, that the landscape will be kind of simple, the training will be easy to find a solution, but then I'll grossly overfit, and then I'll have a very, very little chance to generalize well. So that is the core of the theory of learning for fundamental, right? How to mitigate overfitting such that the training is fine, you will get nice generalization, but it will not overfit. That's the secret, okay? That's the core issue. All right, okay, so how do we address these questions with StatMech? Okay, yeah.
It's easier in the middle. It's easier in the
middle. Oh, okay. Okay, so there are many approaches. Some of them are pioneered by experts here. Chengiz is one of them. Yasaman Bahari will come here later on in the program, is one of them. There are many others. Forgive me for not listing all of them. I want to present to you one approach which I have been involved in together with several co-authors. One of them is Qian-Yi Li, a PhD program at Harvard, sitting here, which is kind of the closest to kind of a StatMech framework. Sometimes it's called Bayesian neural networks, or just StatMech equilibrium approach. So what is this? Basically, we're saying we're not, for the moment, I'm not going to specify the dynamics of the learning, how we find a solution, how we minimize, but we just assume that there's some process and which reaches to the system to equilibrium, statistical mechanic equilibrium. So we define a probability, it's called a posterior probability on the weight space, huge weight space, the number of parameters here, which is going to be a partition function times e to the minus beta times our loss, which I defined here, which I defined over there. So this is the loss, the mean square error here over there. So it's a function, is the constraint from the data on the weight space. This is this loss. And we add one more term here, which is 1 over 2 sigma square times the norm square of all the theta, which just means sum of all the parameters square. So why this? This is a Gaussian prior on the weight space, and it's crucial. And sigma square is the width of this. Sigma is the width of this Gaussian prior. So I mentioned the problem of overfitting, and it turns out, and that's kind of surprising, that there are several ways to bias the network to find a solution that is good for not only for the training but also in generalization. And the simplest one and the most fundamental one is to bias the solutions towards one with small norm. It turns out that this L2 regularizer, as it's called, is doing tremendous amount of the work in mitigating overfitting. There are of course other tricks, and many other tricks to do this, but this is kind of the most fundamental one and the simplest one. Yeah?
When you set up the weight space to look like this, are you making some kind of assumption about your data?
About what?
About the data itself?
The data? Here, the data, define the data. No assumptions about it.
Okay, gotcha.
No assumptions.
So this Gaussian prior is?
No, but the Gaussian prior is on the weight, not on the data. The data are the inputs x mu and the labels the y mu, nothing to do with this, right? But it's good that you mention it because it's important for me to say what we are, our approach at least, there are other approaches, complementary approaches. Our approach is to leave the data as is without making any assumptions of data. Because in my perspective, one of the challenges and one of the achievements of modern statistical mechanics of learning, as compared to what we have done in the 80s and 90s, is precisely this. We're not going to assume IID, we're not going to do random input-output mapping or Gaussians. Whatever the data is, we're just going to fix it. This is why from statistical mechanics you can see that replica approaches and so on are not going to work, because you must make some assumptions about the data. So we're not going to do that.
What about P?
This is a probability.
Not P.
The what?
Number of data.
What? Yeah, so I'll come to it.
U goes from 1 to P.
Yeah, I'll come to it.
Is P fixed forever?
No, I'll come to it. Okay. I'll come to it, okay.
So the norma of theta is
That's some of them are of all the parameters. Some of all the parameters.
How do you define
Some square of all the parameters.
How do you define your temperature in beta?
Temperature is a parameter. Okay, so I'll come to it, okay? So we have beta, we have sigma, we have depth, we have n, then we have the data. So many parameters, okay. So let's talk about beta. Okay, so basically the idea is we are interested, we can do it for any beta. We are interested in the limit of beta goes to infinity or zero temperature, okay? Which means that we are going to be in a regime where there is a solution with L equal to 0. So all the data, all training data are perfectly fit, okay? So, and beta goes to infinity, there is no beta here. So beta goes to infinity means that we're constraining the weight space to that regime of solution. So that's what's known as over-parameterized regime. We are going to assume that the system is big enough such that it can fit all the data perfectly. So if you think about kind of phase space, this is theta 1, this is theta 2, then we have some, big space. It's actually infinite, but let's think about it this way, and where L is 0. And we are, and now the remaining averages that we have to do is within this space of L equal to 0. And here this kick in, because without this it probably would be infinite, but in any case, this biased the averaging here with a Gaussian. So the averaging basically here is in the constrained space of the solution space, you are averaging with a Gaussian prior. That's it. That's what the story is. So, but that's how to do it, and what comes out of it, that's the challenge.
So how is L equals 0 related to beta equals infinity? They're independent, right?
No, because beta equals to infinity forces P to be at the minimum of L. And I'm considering, I'm assuming there is a minimum of L equal to 0, but not only one minimum, but a whole space with finite entropy of a minimum, or of 0 solution. Okay, I'm going to assume the system is large enough such that the minimum of L is 0. But if beta is finite, then even if there is such a solution, you will sample non-solution weights. I'm forcing the system to sample only from the solution space.
But do you expect that region L equals 0 to be continuous manifold?
All right, so that's a good question. It turns out, and I don't want to, okay, maybe I should talk about scaling, but I can already tell you, in the regime that we are talking about, amazingly, this is not, it's not convex, but in most cases, it does look like one. There are saddles, but local minima, I don't know. Maybe some people from my colleagues here can show me examples, but typically it's just no problem. It's not a rough landscape. There is no applicativity breaking, no phase transitions. Just have to do the right lead average and to predict what will be the generalization for that. Okay. There are other formulations where things are more challenging, where work on it, but in this case, That's one of the big kind of conceptual switches that we have to do. Forget about glassy dynamics and so on. If I had glassy dynamics, it's not an interesting problem for learning. That's what my point is. Forget it. The brain doesn't learn with glassy dynamics. So we are in a regime where it's not. All right. Okay, more questions.
On some scale of the infinity of n, L.
Yeah, could be, but no, beta doesn't have any. It may depend on L, but we can start. Yeah. No. We're talking about large N and so on. So I'll come to it in a minute. All right, but before I'm doing that, I want to. Are there questions here?
The distribution of the test data.
Well, this is for given test data. Then you can average on test data. I define it generalization for given test points. Okay. All right. So what are we? So suppose I know how to compute with this. What are we interested in? We're not interested in theta itself. We're interested in this predictor or the generalization error. So if you take this and write down the generalization error, so now we have to, there is no single theta, so there is a whole distribution of theta. So I have to do average over theta. So now I define this as average over theta of f of x given theta minus y of x squared, where I now average over theta. And it's, if you just open it, you can see that there are two terms. One term is the bias, the mean term. So this will be 1/2 the mean of f over theta minus y of x squared, and then the fluctuations on f. Okay? So for a given test point, I already have kind of two contributions, a bias contribution, where the average is with respect to theta, to this weight space, and a variance contribution. So this is the bias and this is the variance, which already means that what we are interested in is at least these quantities. Take this weight space, compute the mean predictor on this weight space for arbitrary point, and the fluctuations of the main of the predictor on arbitrary point. So this is the minimal statistic that you're interested in. Okay, the rest will be bones, but that's what you want. Okay, so all right. Okay, so before going to talk about scales, I want to say one thing. Okay, so if I to compute this, and I can integrate out the readout weights, fixing W. This is easy because F is linear in the readout weights, so L is quadratic in the readout weights. So this is a Gaussian problem on the readout weights, fixing W, right? This is Gaussian, L is Gaussian, so I can just do it. It's just linear regression. Okay, so that's easy to do. And if you do this, you get the following. You get for the mean predictor, now the mean is over A only, the readout weights. You get something like K, I'll define it in a moment. K of X is a vector, depends on W. There is a matrix here, W times the data Y. And the fluctuations of X, again, average over A, is K of W XX minus K of vector of X times the inverse of the matrix W times again KW X. Okay, so what is this K? Okay, so this so I define, and that's the fundamental quantity in the whole theory, is I define a kernel, which is a scalar function of two inputs. You take one input, you take another input, you propagate to the network, you compute for each one of the input the feature representation of that, and you take the dot product of them. That's it. So this is simply 1 over n times sum over I from 1 to n of x, I, L of input x, I, L of input x prime. The dot product of the representation of the network from two inputs. That's the matrix K. That's the function K. So that's the kernel. This one, the matrix is this applied to the data. So it's P by P. This one is K vector Wx is, for index mu is the kernel on x mu and x the test point. So the matrix is x mu, x nu is on the data, y is a vector of the labels on the data, and this one is the vector where one index is the data and the other one is the x. So it's basically a dot product between each one of the data point, the training data, and a new point x. Okay, so that's basically the fundamental quantity is this kernel. For arbitrary two inputs, you construct the P by P matrix, the data kernel, by putting here a pair of inputs, and this vector is just one of the data point, training data, and an arbitrary point x.
So the x's are just real numbers.
That what?
Real numbers.
Everything is real numbers.
Minus
Everything here is real numbers. This, again, real numbers. Okay, so that's easy to prove. It's a linear regression. There is nothing, okay? That's expression. So I can use this, I can put it here, compute generalization. But that's, of course, linear regression, not interesting. So the interesting question is, hey, all these are depends on W. I just integrated A. So what happens for W? How do I go beyond? How do I integrate out W? This is where the heart of the problem is, how to do the integration of W. This is a nonlinear problem, and highly nonlinear, many parameters, and challenging. Okay, so here comes the scales that David was very worried about correctly. Okay, so I need this, so I'll erase it here. So one limit is what's known as infinite width limit. In the infinite width limit, you take n goes to infinity, you fix L, some number, n goes to infinity, but P, and let's say L, everything else is finite. Okay, so that's the number of training points is finite, n goes to infinity. Okay, that is a well-known limit that basically what happens if things are simple. What simple is you average W by replacing each one of these kernels by the average kernel. By averaging, I mean on the prior, on the Gaussian. So basically, every time you have a kernel, you replace the kernel basically by average of XL of W I square root of n x L minus 1 times, so this is like phi, times the other phi, where you have dot dot dot, x prime L minus 1, and you average over W. Okay, so there are many W's here, but you average over W Gaussian. So basically, you assume W is not learned. Okay, so W is just the prior, just is sampled from the prior here, just Gaussians, IID Gaussians, and you average this. And there are ways to do it iteratively, so you can average the first layer, the second layer, or from the top layer, and so on and so forth. So everything now is simple. There are, for some models, there are explicit expressions for that. That's known as Gaussian process kernel. W is gone, and you just average this, all the matrices W Gaussian, IID Gaussian. Okay? So now the thing is simple. So now I go back to here. I average over all theta. I replace this by the Gaussian process, by the Gaussian process here, by the Gaussian process here, by the Gaussian process here, and everything is fine. So there are two things. There are several assumptions which prove to be exact in this limit. One of them that the prior is good enough, but the other one is that it's kind of self-averaging, that you can do the average kind of step by step, and you don't have to worry about the average of the inverse is the, etc., etc. So every time you have a kernel, you just replace it by this. Okay, good. So that's known as the infinite width limit. And it's nice, it has properties. It's amazing that it still gives some non-trivial results for the generalization. And you could imagine how can it be? But again, the answer is for sigma small, for this Gaussian prior, if it's small enough, it can give you in many cases non-trivial generalization error. So it's not completely overfitting, despite the fact that the system is kind of infinite and p small. So that's in the same spirit that the generalization is in some sense simpler than what we thought. Okay? We were always worried the system is too big, then it overfit. Well, if you have a very simple inductive bias like the Gaussian, even the system is infinite, it's not bad. However, this is not, of course, not enough. The size p is fixed, n is infinity, there is no n dependence, but there is no also data dependence, because if you think about this, then it means basically it replaces the system by w, which is not learned. You just sample w from Gaussian, and all the only learning is in A. Okay? Now this, for p fixed is fine, but what happens if p is large? Or in particular, what happens if p is larger than n? So let's go back to here. Oh, wow. I don't know what's happening here. Okay. Okay, what happens if p is larger than n? Okay, then obviously the system fails because you have more constraints than number of a's, and the system won't be able to learn. So the only way to learn is to modify w. Okay, so so obviously when p is not fixed and goes to infinity, but p scales with n, then things are more complex. So what we are interested in what's known as the linear regime, where p is alpha times n. Okay? So n goes to infinity, p goes to infinity, but alpha is order 1. And we knew all along that stat mech of this is where the action is in. Okay, so how do we do this? So what happens here? All right, so what we found is, for this problem, which is much harder, I'm going to describe briefly what is called backpropagating, what we call backpropagating kernel renormalization. Okay, so
L is kept fixed.
what?
L is fixed, or it can also stay.
That what?
L.
L is fixed. Yeah, L is fixed. All right. So oh, what's going on? Okay. Okay, I want to add. Okay, so here we said everything is the Gaussian process kernel. I want to add one more equation than f of x, and this is the norm of weights before going. So if I compute this mean square error and compute the norm of weights, I'll find, normalized by n, I'll find that it is, in general, 1 minus alpha times sigma square times y transpose, the inverse kernel is a function of w, y sigma square over n. This is before averaging over w. If you look at what comes out of the norm of the readout weights, what you get is that this is the fluctuations if the alpha is p over n. So this is the number of dimensions which are in the null space of the data, because you have only p. This is n minus p. So this is just the Gaussian fluctuations norm, and this is coming from the constraints, from learning the data. So this is kind of dimension p, and this is dimension n minus p. And now in the infinite width limit, of course, you don't have alpha, and you replace this by w by Gaussian process, and that's it. But it's small corrections. So in the renormalization group, what we do is the following: we take the network and we say, okay, we integrated A, and we got what we have. So this was A here, this was W here, this was W. I'm going back to W, etc. And we integrate out only one layer, leaving the others. And what we find that after integrating one layer, so now we're integrating W1, let's call it. Okay? What we find is that after integrating W1, we get the remaining W here. But the integration of W1, what it does, it introduces the K after integrating W1 becomes the KGP kernel times, times a constant U, a renormalization constant. Basically, okay, let me go to the integrate. When we integrate all K's, it's simpler to say when we're integrating all W, because I don't have time to talk about step by step. If we integrate all W, so instead of replacing KW, but KGP, we're replacing the Gaussian process by a renormalization U to the L. And in this U, is basically, you can think about the kernel as every averaging over W gives you an extra factor of U. U is simply renormalizes the kernel, a scalar renormalization of the kernel. So it's a very simple modification of the infinite width limit, but this parameter U, which now will replace everything here by this parameter U, is basically the self-consistent equation for the readout weights. So basically what we have is this is U. This is now the Gaussian process divided by U to the L, because we're doing L integrations. And this gives us a self-consistent equation for U. So basically what you find is that the kernels, the Gaussian process kernels, are renormalized by a renormalization U, which every time you do the integration of a W, you just multiply by, you just raise it to the power U. But now this U is a highly non-trivial quantity because it depends on alpha, but also it depends on the data. Y is the labels, K is the input. So it has a lot of information about the data, about the full data. Yes.
How do you know what L should be?
L, parameter, hyperparameter.
Okay. Gotcha.
Okay.
So you just
I just use. So it's an important question. You can ask what happens as a function of L, whether, you know, how generalization work with L. We can discuss it, but for now it's a parameter. Yes.
So when you integrate out one layer, you do it with respect to the measure that's defined by only the prior.
So what?
Also the error?
No. So if you go back to the statistical mechanics, you can integrate out one layer, and then keep the other ones.
But you integrate with respect to the full measure, not just with the
Yeah,
different
right. You integrate out with the posterior of W, exactly. And then you find that you scale it by U, and then you keep doing it, and you get this all the parameters.
So that explains it. How did you get U on the left-hand side there?
No, the theory says that this renormalization factor U is the self-consistent readout weights. That's a result of the theory. And therefore, the U is, this is the interpretation of this equation. U, the order parameter U, the renormalization factor, is basically, you basically project the norm of A down to the, you backpropagate the norm of A to the first layer. And this norm of A is, again, this is the trivial thing, the fluctuations, and this is now the self-consistent part. This is the inverse kernel renormalized by U to the L. So this is a self-consistent algebraic equation for the order parameter U. And you can compute it as a function of alpha. You can compute it as a function of L for the data, whatever it is. Yes?
So am I understanding correctly that you're basically making then, after integrating out an approximation where you say that sort of after the integration you still sort of project back to the closest Gaussian process approximation? Because, I mean, in principle...
No, I don't know. I mean, okay, so we can discuss, I'll discuss in a minute. Well, I don't have much, but, you know, what is the, you know, for now, think about it as an exact solution of the problem. Just computing the true posterior for the predictor, for instance, by integrate out all the weights. Okay?
You call this back propagation?
Because the way we do it is by integrating from here. We integrate first A, then W, then this, so kind of back propagating. That's the way we renormalize it out. We renormalize it from the top to the bottom. You can do it also the other way around, but that's, we'll find the simplest one. Yes?
In this case, should I consider k minus 1 as the average of k, our inverse of that, or the average of the...
We are computing the mean predictor, and whatever comes out of it is this. Okay, we're not computing k and inverting it, no. We're just computing the true mean predictor coming out of integrating W, and the result is that you replace this by the renormalized kernel. Okay, so let me say a few words about it because I see time's out. One is that when you replace this by the renormalized kernel, in the simplest case, the factor of U on the mean predictor drops because you have k here and you have inverse k. Okay, so the mean predictor doesn't change. It's basically the Gaussian process. Here, it is scaled linearly with k. So the renormalization is on the variance, not on the mean. So the mean is the same as the Gaussian process. The variance now is scaled with U. The variance is doing the job. Okay? Just one moment. Okay? But I want to say this is only in the simplest architecture. In the more general architecture and more modern architectures, networks f of x have multiple pathways converging on them. So imagine you have something like sum over L, AL, these are vectors, AL transpose times X, not L, let's call it, I don't know, M1 to something, and then you have here X of W, M, and so on. So imagine that you have multiple pathways that converge on F, and they have different structure. For instance, they may have different nonlinearities, like skip connections. One of them may have convolution, another one may have not, or graphs of different degrees, etc., etc. So if you do this, then you find that in the renormalized theory, the mean predictor will be sum over L, the effective kernel that comes into the predictor will be sum over M times different predictor for each one of them times UM. So there are many cases, interesting cases, where where you have multiple separate renormalization factor for each one of these pathways. And in this case, the mean predictor already will be non-trivially renormalized because it's not simply, you know, in K, it's not a scalar normalization. You change the shape of the kernel by different scaling of the different information pathway coming to it. Okay? So that's kind of several examples that we have worked or we are working on where you can see that. Okay? So the finite alpha regime is shaping or scaling the importance of the relative importance of the different pathways in the system. Okay, there were several questions over there. Yes? Can you speak up louder?
Yeah. The physical intuition behind integrating out the weights in this case, is it just to get an kernel for the system, or is there more reasons why you want to take this technique?
No, to integrate of the weights is what we have to do, right? We have a whole space of solutions, and we're interested in the statistics of predictor, variance of predictor, whatever. So we have to do the average. Integrate out the weight means averaging over the weights. We have the posterior on the weights. It's not a single weight. We're not running some learning and find W. We are just integrating over all the posterior of the weight space. Integrate out, I mean averaging with respect to the correct posterior. Okay, time is short. Let me just make a few comments. First of all, how exact is this? Okay, so for a linear case, the problem is still nonlinear because the loss is a function of product of W. So the weight space is not governed by a quadratic. It's not a Gaussian problem, even if phi is linear. But the algebra that we do is exact in this case, in what I define as the linear. So that is exact, okay, in this thermodynamic limit, in this linear regime. But of course, the interesting stuff is when nuance are nonlinear, when the input-output function is nonlinear. So what happens if phi is Gaussian? I'm sorry, is like a ReLU, right? Rectified linear. Let's see. As an example, or a simplest example maybe of nonlinearity. So in that case, basically, we don't have exact solution. What we do is basically approximate this as Gaussian, phi is Gaussian, and fitting the first two moments of this Gaussian by the correct first two moments of this. So we have phi mu, phi nu, this will be the covariance, phi mu average will be the mean, and we replace this, the phi of z, by a Gaussian with the correct first two moments, okay? That's what we do. And amazingly, we find a fantastic fit of this theory when this is now the Gaussian process kernel of a nonlinear, let's say, ReLU, with the numerics. So you see in the paper, we show examples, and it caught us by surprise. What's going on? This is approximation, ad hoc, in the kind of spirit of physics. Okay, what can we do? Okay, let's assume it's Gaussian. But we also found regimes where it fails, particularly L. When L goes beyond 5 and 6 and so on, we start to see deviations. It has also to do with alpha. When alpha is too big, we start to see deviations. So there are papers on that. Some papers claim this conjecture is exact, whatever. We don't believe it's simply as simple as that. But there are conditions, and we have here a local expert on random processes and random matrices and Gaussians and so on. And I think this part of what I would like to achieve in this program is to understand better under what conditions this Gaussian approximation is actually. Now, the last point which I want to say is about feature learning, which is a big thing in the field, and this is what can we say beyond the generalization and performance about what comes out in the feature layer after learning. What have they learned? So in the infinite width limit, there is no learning. This is just random, and you read out from these random features. Here, there is learning. So how this learning actually reflects itself if you look at the feature layer? And the answer is interesting. The answer is, so the learning is the following. So if I look at let's say at the pre-activation, at the input of the feature layer, Z, what I call ZL, okay, for some input x mu, and ask how this looks like. What is the statistics of it? So it turns out the first term, you know, and this is for, I don't know, neuron I. The first term is just the Gaussian. It's just the prior. So this is just Gaussian with the correct variant. That's all. Okay? So there is no learning. This will be like the infinite width limit. Like the feature, everything is Gaussian. But then there is correction, which comes with 1 over square root of n, which I'm writing it for multiple outputs. Imagine you have multiple outputs. And then you have here some random Gaussian m times ym mu. So this is a low-rank structure. This is Gaussians with non-trivial covariant, which has to do with the parameter u. Okay, so there is non-trivial covariance of this w. So for each one of the output of the network, there is a contribution of rank 1 to the feature layer. So this is where the action is. This is where there is a feature learning. This is just prior Gaussian, and here are the contribution for feature learning. And I'm emphasizing it because of the following. This is 1 over square root of n. So in the language of StatMech, this will be finite width, finite n correction. But this finite n correction cannot, for finite alpha, cannot be neglected, because this is what is doing the job of learning. So for instance, when alpha is finite, then the readout weights are really tapping on this, not on this. So this is crucial to the learning. You cannot ignore it, okay? So the take-home message is that when we do StatMech on these systems, very often, I claim, we have to look at finite n corrections, because there are cases where if you ignore them, you miss a very important part of the story. And in this case, feature learning, which is crucial in this case for the readout to be successful, is tapped by finite n1 over square n correction. So to wrap it up, you can see here how we are back into, in my view, the very important and relevant regime and realistic regime where data and width of the network is linear. We are trying to do, and to some extent achieving, a way to do statistical mechanics without making strong assumptions of the data. It's not ID data, it's whatever it is, MNIST, ImageNet, whatever. To some extent, maybe for this we have to do more. We are able to do, or at least we have a roadmap to do, not only computing generalization and performance, but also to understand what kind of properties of the solution that emerges from it by this type of calculation. But there are many challenges. So one of them I mentioned, to understand the limitations or how much we can push for the nonlinear case. Another one is, I mentioned at the beginning, more complex and more modern architectures, recurrent neural networks, transformers, etc., etc. So there are many, many, this is just the beginning of something which I believe should be and will be a very fruitful area of theory, not only coming from physics, but I think statistical physics will be a very important contribution to this. Thank you. Yeah.
Could you give an example of an empirical result that you could explain with this theory that wasn't explained by the infinitely wide theory?
Well, the dependence on width. Infinite width, there is no, you look at a real network and you change the size of the network.
You mentioned that you had very good correspondence in some graphs in your paper. Well, so did you...
You take whatever, you take MNIST, CIFAR, or some whatever, and you train a neural network to learn it, and you compute the generalization of it. as a function of the width. In a real neural network, the width is finite, it's not infinite. Okay?
Okay, so you could really explain the graph better.
Exactly, the N dependence, the L dependence, the dependence on the non-trivial and nonlinear dependence on the bias sigma, which in the case of infinite width is simply sigma to the power 2L, just trivial scaling. Here it is very non-trivial. So there are many results here which you can compare with a real network which have finite sizes and huge amount of data, which linear scaling is much more, explain it much better.
Yeah, how should I think about capacity in this setting? So you don't have everything, like worst case?
Capacity, so that's a good question. For nonlinear system, there have been a lot of work on capacity, at least attempts. I would say, kind of in a very crude way, you can think about capacity in terms of random input-outputs, right? That's what I mean by capacity. That's what I define by capacity. You have some random input-output. How many of them you can store?
But how random? Like, then you have to assume model for the random.
That what?
Then you say random input output, then you have to assume a model for the input, right?
Random Gaussian input and random. I'm just defining capacity. It's not about learning.
So in this case, you don't have. So in this case, where you have a fixed input, but you say or like the input is just.
No, I'm just okay. We can discuss it offline. I'm just saying capacity will be simply if I define capacity as how much memory I can store in this system, then I would say it scales with the more or less with the number of parameters in the system. So it's not in this regime. P is alpha n. P doesn't scale with the number of parameters. The number of parameters is n to the L and so on and so forth. We are way above, well, way below capacity, okay? But it turns out, and I believe for good reasons, the relevant regime in the deep network is not P linear with the capacity. It's P linear with the width, which is a very important, very different limit. There is statistical mechanics also in polynomial, but and there will be interesting statistical mechanics there. And in some cases, in single layer, we actually see what happens. Divergences, we are close to the capacity. And but I myself don't think that in the big picture this is the interesting regime. I think networks have, well, I don't know about large language models, but networks for vision and others, the number of parameters is much larger than the number of examples.
Two more questions.
Yeah.
So you took the limit of infinite width. What is known about the limit of infinite depth, taking L to infinity?
There are some beautiful works about infinite width and infinite depth. I think Chengiz is one of them. I don't know. We considered infinite L limit, but first taking n and p to infinity in this regime, and then take L to infinity. And they're interesting. They're interesting critical values. The interesting phenomena. What happens when L is large? It's an interesting limit. But we are not doing it together with n. We're doing it separately. N first, and then L goes to infinity.
Yeah, so you said that you were sort of reluctant to make assumptions on the data. So I'm a bit confused because there are these no free lunch theorems which say that you don't make any assumptions on sort of the process that generates your data. You cannot really make any sort of strong guarantees on how much you will learn, right? So.
Well, I don't know about this no free lunch. I hope I'll have free lunch soon. But when I'm saying that I don't have, there is a price for not making assumptions on the data, and this is that what I call generalization is per test point. Okay, so you can ask, okay, but I want to know the average generalization. So in the average generalization, you will have to make some assumptions about the generator of the data, the training data. You want to average over that perhaps also, but definitely you want to average over a test point with some generative model relative to the data. So ultimately, if you have some problem to solve, you will have to go beyond point-wise generalization. Okay, that definitely. But in my view, that comes later. Okay, now I'm giving you generalization for each one of the arbitrary test points. Take this and make assumptions about the data or about the test data and plug it in and do the average. Okay, there is a price to pay for this. I agree.
Okay, time for your free lunch.
Okay, thank you.